Okay, it looks like we still have some people joining us, but we'll go ahead and get started. Good afternoon, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on sustainable solutions. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your day to attend. While we're waiting for people to continue to join, a few quick housekeeping items. Everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask your question verbally, please raise your hand in the toolbar and I will unmute you and call on you to ask your question out loud. If your question does not get answered right away, we will address it at the end of the webinar. You can access and download PDF copies of this presentation, our product line card, our sustainable one-pager, and information on our technical engineering team in the handout section during the presentation. If you are attending live, a certificate of completion and recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF of the presentation and handouts. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page. You can now subscribe or invite your coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars as well on this page. Another great technical resource is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the home page. In addition to our presenter, Andrea Kendrick, who I will introduce here in just a moment, we also have Jason Merkel, Technical Manager, on hand to answer your questions today. At this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise she brings to the table. Without further ado, Andrea.
Hello, everybody. Welcome to our webinar today. I will be going over sustainable solutions. So our agenda for today, we'll talk a few definitions: circular economy, bioplastics. Then we'll get into the recycling processes. We'll talk a little bit about greenhouse gases and the emissions. We'll also go over the sustainable materials, some examples of those materials that exist. And then we'll go over some trends that are being seen kind of right now in the market. So before we have this conversation about some of the solutions, I want to give you guys an understanding of these terms. We actually did do a sustainable presentation about a year and a few months ago. And even since then, we have more terms and more common terms that are being used. And so I want to make sure that we're keeping everybody up to date on those and what some of those terms are. So starting with circular economy. So you'll hear that a lot. It's kind of a newer buzzword, if you will. So circular economy is really the idea that materials are being used, not used up or wasted. Products and systems are being designed so that we're not losing material, we're not creating or releasing toxic materials, and we're achieving the optimum use of our materials, processes, and components. So some of the ways that we do that, you've probably heard a lot of the reduce, reuse, recycle. Those are a lot of the ones that we kind of go after, some of the approaches. So reduce is just overall material design. So maybe we're making a little bit thinner, maybe we're getting rid of some of design features that are unnecessary to save on material usage. We'd be reusing stuff. So if we're using products that can be used again for the same purpose, so maybe you have your own process and then you reintroduce a little bit of the regrind into it. So something like that. Recover, this would be something where we could use waste in place of a different material. So maybe using a different product in place of that. And then recycle would be what we're commonly hearing a lot, is we're recovering materials to then be reused back into either the same application or different applications. And so it doesn't end up in the landfill. Okay. Bioplastics, so this one we did talk about. It's kind of the overarching term that we would use. Bioplastics simply describes any type of material that's going to come from renewable resources, biodegradable, or both. So really anything that falls under the green scope or sustainable plastics would be called bioplastics. So then the big one you're going to hear a lot, bio-based. This is getting a lot of traction in developments for materials. So bio-based products are going to be the beginning of life. So when we actually make the products, these are materials that are using renewable carbons. So instead of using your standard petro or fossil fuel-based carbons, we're replacing them with what are typically plant-based carbons. And then in these cases, for the majority of these materials, because they are still carbon atoms, regardless of where you get them from, the performance of these materials are going to be that and comparable to standard plastics. So a few different terms that maybe you'll hear, maybe different agencies will use different terminology that you might hear. But if we're talking bio-based, bio-raw material, which is slightly different than bio-circular, which I'll touch on next. So your bio would be starting the very beginning. We would use stuff like corn, maybe it's industrial corn that doesn't have use for feed, sugarcane, cotton, canola. We're using that to actually make our materials. So those are the carbons that are then replacing the fossil-based ones in our standard plastics. So these would be any materials with feedstocks derived all or partially from virgin biomass, which is slightly different than biocircular in that you'd be using biological origin waste and residuals. So instead of something that was maybe grown, so maybe the industrial corn is grown specifically for those bio-based resins, these would be waste products from stuff like any type of forestry process, tall oil from paper manufacturing, where they're using this waste that would have just been thrown out to reintroduce back into the process to make a material. So these are also considered bio-based as well, because it's in the beginning and partially renewable bio content for these materials. Okay, and then a biocomposite, which is kind of similar. The only real difference is you've already made the product, so maybe it's a propylene or an ethylene, and then you're including reinforcing agents that are biomaterials like wood, flax, hemp, stuff of that nature. So instead of using glass, maybe we're using a renewable resource like the wood, the hemp, as a reinforcing agent instead. These ones tend to give you some of the property improvements that you would see with glass, so stuff like maybe a stiffness and strength improvement. It just won't be to the same level that you'll achieve with glass, but you still get the renewable source, the green aspect of these materials as well. Okay, then we move on to biodegradable, which is a different kind of section of our bioplastics. This has to do with the end of life. So now we were just talking about beginning of life and making materials at the start of the process. Now this is more at the end of the life. So I'm done with the product. What do I do with it now? So these are materials that can undergo biodegradation. So this is the chemical process. Microorganisms will convert them into natural substances like your water, carbon dioxide, and compost. And so most of these are going to be starch-based materials. And so because of that, though, you will get a little bit of a difference in performance. So your bio-based ones, being that they're just carbons are being switched out, generally you have similar performance. In this case with biodegradable, you do see a shift in performance. And at the end of the presentation, I do have some tables that kind of show your performance differences of the different materials. Okay, and then there's a subset within biodegradable, which is compostable. And so this has a very distinct term that means that it undergoes a certain test and it has to compost after a certain amount of time under certain conditions. And so if you see a material that's been certified compostable, it means that it's adhering to a certain standard. In the US, it's the D6400. In Europe, it's the 13432. And it just means that after 180 days with certain conditions, it's going to compost down a certain amount. These are interesting to look for too, because if a product is being marketed that, it's great. It does have that end of life aspect where it takes it back in instead of being sent to landfills or to be incinerated. The issue with it is if it's a consumer product, most areas don't have industrial composting facilities for you to just send it to. So you can't just send it in with your, recyclable stuff or compost it in your backyard. It has to go to an actual facility. So keep that in mind as well. Okay. And then we have circular or recycled. Again, kind of bringing up the circular quite a bit. It's gaining quite a lot of traction in terms of the terms that we're using. So circular, or what we've previously always just called reprocessed or recycled. So the couple that fall under that would be your post-industrial. Another term that is gaining some traction as well as pre-consumer. So we call it most of the time, and I myself personally call it post-industrial, but pre-consumer is gaining some traction as well. This refers to the material that's been generated as a waste stream from a manufacturer's process. So a manufacturer went to make a part, maybe it's a short shot, maybe it didn't come out the way they wanted it to. That then gets used as the feedstock to create this post-industrial product. And then post-consumer, PCR, this would be material that's generated from households or end-use facilities where it's already been in use. Maybe it's a water bottle, maybe it's carpet backing, it's already been used, and then it comes back into the feed stream and recycled to be used for new products. Okay. So when we talk recycling, circular recycling, there's a few different ways of doing it. So I want to touch on some of them, specifically chemical, and we'll talk about it even more because it's gaining quite a bit of traction. There's not always a ton of information out there on it. So mechanical is going to be the one that, generally speaking, we're most familiar with. So it's going to be, we simply process it down, it goes through a physical change, grind it up, sort it, repelletize it, and it's just a physical change. Nothing crazy is happening to it. Now, the two other ways of doing this would be dissolution is one. This is where you're going to dissolve the product down with a solvent, and then the polymer is going to be separated from any additives, fillers, or anything you might have added to it. So that way you can recover the polymer and recreate that polymer, same polymer as it was. And then on the last one would be your chemical recycling, and this is where we're going to depolymerize it and then repolymerize it most of the time into a completely new polymer. And so it goes completely through a chemical change. So we'll talk about them a little bit more as we go through, but these would be when you say it's a recycled product, it has gone through one of these processes. Okay. So chemical versus mechanical. So again, most familiar with mechanical. So your process, you're going to collect it. It's going to be ground down. We're going to wash it, sort it. Then it's just going to go through the standard processing, pelletizing it, compounding, manufacturing it. And then I say consumer use optional because if it's PCR versus PIR, may or may not have gotten into the hands of the consumer. We're not sure. Mechanical really is the preferred method if your overall end goal is to have more reduction for greenhouse gases. The problem being though, because it's initial heat history and we're just repelletizing it, it does have a little bit lower quality and lower performance. But if your application can handle that, and the bigger aspect is the green emission reduction aspect, perfect option for you. On the other side, chemical, which is gaining a little more traction, sometimes it's called feedstock recycling. There's additional steps where we're actually going to depolymerize it and repolymerize it. So those have been called out specifically here. Now, when we do that, depolymerizing it, the most common method that you're going to see is pyrolysis. So this is going to be a thermal process that's going to convert your carbon-based substances, because you can do more than just plastic with this process, but for us, plastic. And it's converted into char, tar, and gas, from which we can then use some of that for added features. So what that looks like would be this little drawing here. Plastic goes in, the water bottles go in, it goes through the process, and then it has different outputs. So process is it's heated up, generally around 500 C. There is a range, you can do it at different temperatures, but typically around 500 C gives you the best pyrolysis oil output. So that's what most companies tend to run it at. You also, when this is done, it's in the absence of oxygen, so there's no combusting. So the combustible gases, which are a product of this after the polymer decomposes, they don't combust and start to blow up. So there's no oxygen, so it allows that to happen. So the creation after the polymer decomposes is combustible gases, non-condensable gases, and then biochar are created. So it's going to be kind of your three little pictures down here showing that. And then we condense the gases. So the ones that can be condensed down do get condensed down into useful liquids. That's what gives you your pyrolysis oil. And then the non-condensable gases, your syngas remains, that actually then is used. So the byproducts are being used now. The gas can be put back into the system. So it's actually a fairly efficient system. It's a little more sustainable by itself because some of the byproducts get put back in to keep it running. So basically your syngas goes back in to heat the furnace to then heat the next section of material that you're going to use. And then we introduce the pyrolysis oil and naphtha back in to create new polymers. So that looks a little something like this. So your standard process would be your gases come in, then you have a cracking process, polymerization, polymer. In this case, when we're using bio-based ones with material that have gone through pyrolysis, you introduce the oil here with the gas, and then it goes through the same process, cracking, polymerization, polymer. And so that's what gives you your bio or green component, is using those gases from recycled material that already existed. Okay. And so some notes to that or things to look for is that if you're using this oil in a really large quantity, so let's say you get a bunch out and then you want to introduce it at a certain percentage compared to the other oils that we're using, is that if you use it over a certain amount, generally about 20%, you have to purify it. And so the idea is your chemical recycling is already a little limited in terms of the amount of savings you get for greenhouse gas emissions. So you get less, it is less than your standard conventional, but if you start using a lot of oil and it has to go through an additional process, now you're starting to create another emission, or there's more emissions being done because of the new process. So you actually start to see a limitation. You still generally see an improvement overall, but just keep that in mind that there might be a reason why there's only a certain percentage of green in your product, and it might be because of this specifically. And so recent studies that have been done have found that about 5% of the pyrolysis oil is best to give you the best emission savings. So you get about 20% emission savings, making a couple of olefins, high density and low density polyethylene, when you use 5%, because it does not need to go through that additional process. So here kind of gives you that data here. So standard at 133, and then down in the 1.32-ish range, and then 1.318-ish, and then 3.2-ish. So again, still an improvement, but you start to actually lose a little bit of your savings going to a higher percentage of the oil. So keep that in mind when we're looking at, and the end goal maybe being that you're saving on your emissions. Okay. So we say emissions, we say this, maybe we're not familiar with all of this and what this means. So greenhouse gases is kind of what we're talking about here. So your greenhouse gases are going to be ones that trap heat in the atmosphere. And so they're being used, or they exist, and they are warming the planet. So they're responsible for global warming. And so how now these gases do that, or how effective they are, depends on a few different things. The first one being how much of the gas is present. If you have a lot more of the gas present, obviously it's going to trap more heat. It's going to warm it even more. Then you have how long it's going to remain in the atmosphere. So the gas is here, or we created it, because carbon dioxide, which we'll talk about, can be created. And so how long is it going to stay? Is it staying for 100 years? Is it staying for less? So that affects it. And then lastly, how effective it is at trapping heat. So if it traps heat even more than others, it's going to affect it more than others. And what you can see here in these charts over here provided by the EPA, carbon dioxide is the lowest, it's the least efficient at trapping heat. The other ones are a lot more effective at doing it. However, there's a lot more carbon dioxide here, and it's more readily produced by us. And so that's what we use when we talk about greenhouse gas emissions. Generally, you see it at CO2 equations, and this is why, because it's most here, which I have here as well. So carbon dioxide is accounting for 2/3 of the total heating influence of all human-produced greenhouse gases. Some of the greenhouse gases are not human-produced, so obviously we're not really as concerned with it because we have less effect when it comes to heating the planet with those ones. And because it's the biggest influence, it is used as the standard for global warming. So generally when you're seeing greenhouse gas emission testing, it's per CO2. Doesn't mean they won't do other ones, but that's just generally the standard one that you'll see. And then this chart provided by NASA is giving us our amount of CO2 in the atmosphere. As of right now, or like yesterday when I checked it last, it was at 420 parts per million. So it had just hit that threshold. So quite a bit more CO2 than the other gases around. So some other examples of kind of what that looks like in terms of testing. So you kind of saw the one with the high density polyethylene and then using bio-based oil and not. There's a couple other ones. There was a study done by NAPCOR, a life cycle analysis done comparing plastic, aluminum, and glass. And it shows for the same-ish amount of liquid, that glass has over 4 times the global warming potential than PET does. And that's being because you have to process aluminum and glass at much higher temperatures. And so the process and the amount of energy needed to heat something up that high is what causes this effect specifically. And then also another one is going to be virgin versus recycled SBS. So a styrenic based TPE, you're looking at the same hardness. You go from a virgin and then you move down to 20% recycled content, 40% recycled content, up to a 40% reduction in GWP. So again, this is why we're talking about these sustainable plastics and their effect on global warming and greenhouse gases. This just gives you an idea of what that looks like and why you might look to use something that's recycled or sustainable. Okay. The next one is going to be, you probably hear a lot of companies, maybe your own company has these goals for sustainability, and maybe you've heard them, but you don't know what they mean. So there's 2 big ones that we hear pretty commonly. Biggest one going to be carbon neutral or carbon neutrality goal. And so that really means that whatever CO2 that's given off as a process or an activity that the company does is being reduced equal to that. So we're at 0 for emission versus how much we're reducing it by. And so we can achieve this by using renewable energy. So a lot of large manufacturing companies have looked to use renewable energy to lower that value, as well as using sustainable feedstocks. So using your bio-based stuff like we saw with the oil, using your recycled content material, stuff like that will start to bring your values down and help you reach your carbon neutral goal. The next one that you might hear, it's not as common, but you might hear net zero. So some companies, some large companies have goals like this. And so it's like carbon neutral, but it includes all of the greenhouse gases. So your carbon neutral goal is just to reduce CO2. Net zero is all of your greenhouse gases. And so it's gonna be your methane, nitric oxide, fluorinated gases, water vapor, all of it to be equal. Most companies you'll see have carbon neutrality goals, not as many have net zero goals, but you might see that start to pop up here and there and become a little more common. Okay. Some things to consider when we're talking about it. So now we kind of understand the terms. Now we're gonna start talking about the materials a little bit. So things we're gonna have to consider, things we're gonna have to think about as we're looking to maybe utilize these or to hit some sustainable goals and what we can do to do that. So the first thing is gonna be cost. And so you've probably heard it, the cost is gonna be a big thing, and cost is a big thing regardless of if it's sustainable or not. But the really big thing that we want you to consider is being that it's a sustainable product does not mean, and most of the time it's the opposite, that it will cost less. Most of the time, especially bio-based products, are gonna actually cost generally more. And so if you're looking to do it and you have a goal to be carbon neutral or you have certain emission goals you're trying to hit, you're gonna have to use these types of products to achieve that. But just know that when you come and you ask for these products, it doesn't mean that they're gonna necessarily cost less. And that's been quite a hindrance to some companies because they see that it's gonna cost so much more for certain things and they go, maybe in a couple of years we'll revisit because we're not in the business to spend more money at this point for our products. Some other things to consider, color. So if you're using recycled materials, specifically or mechanically recycled, it might be difficult to hit certain colors, especially since a lot of feed streams are gonna come in black. So if you come and you say, I need a very bright pink, we're gonna go, well, we have black. So there will be some limitations on your color ability. And I have a little chart that kind of shows that, but just know that you might be limited. And again, most commonly with your mechanical, your recycled materials. Performance, your bio-based materials, as I mentioned, because you're just replacing the carbon, going to be pretty similar. But if we're using mechanically recycled grades or your biodegradable grades, you're going to see that there's going to be a little bit of a difference in performance. And so we have to figure out if that's going to be okay to accept that difference in maybe mechanical performance or heat performance. Next would be recycled requirements. So are there requirements that you use a certain amount of products that are recycled? Is it important, or does the application need to have a certain amount of recycled content? And so stuff like that are to be considered if you're being asked for that. Do you need to have these materials available or to be using these materials? And then lastly, recyclability. So this one gets a little interesting, but stuff like if you're making something, but you also want it to be sustainable, but you also need to still code it like your other recycled products. So sometimes maybe you need the recycling code 1 for PET, so you need to be the same as the water bottle, but maybe it's a chemical recycled grade and it's slightly different, so it can't be a 1. But maybe you need it to be done like that. There are products that do meet that, but it's just one of the things to consider and make sure that we know, ahead of time if that's something we have to meet for you. All right, so a little bit of a, we consider maybe a little bit of an eye chart, a lot to look at, but I wanted to give some general ideas of some of the materials that fall under the different categories that I spoke about. And so that way you get an idea of kind of what could be expected when you ask for certain things. So bio-based, as we talked about, being that it's beginning of life, we're changing out carbons. And then I also included biocomposites in there because the fillers then are of bio nature. So the big ones and stuff that you'd see pretty commonly would be stuff that's made out of maybe castor bean oil. So this would be your polyamide 610s, your 610s, your 1010s, 1012s, whole bunch of them that would come in that nature. If it's a nylon, anything that has a 10 in it, it would be bio-based. If it is made maybe with corn, so this would be your polyamide 5/6s. So anything with a 5 in it would also be similar. It'd be bio-based in nature because of that carbon source being from corn. Polymers that are made from tall oil. So we talked about tall oil being one of the waste products of paper manufacturing. So polymers that are made with that, PEI. So you can make bio-based PEI out of that. And then biocomposite. So this would be anything that's reinforced with waste. So propylene with rice husks. And so that would be under bio-based as well. And again, please remember, there are so many options available. I'm just going over a few maybe common ones or maybe some that you've heard of. We do have an extensive list of them and there's a lot out there. And so our one pager would kind of help maybe navigate you a little bit on that, but just know that I want to touch base on some of them. Biodegradable, again, it's kind of its own special little section. Compostable or biodegradable, generally they're starch-based. So there's compostable elastomers, there's compostable and biodegradable other products that are maybe nylon-based or propylene-based. Those all exist. And so you could get those if the idea is end use, it doesn't end up in the landfill. And then your circular ones, so your reprocessed ones, PIR, PCR. And so propylene made from mechanically recycling shampoo bottles that were recycled back in, PBT that's been made from chemically recycled PET bottles. So that would be your chemical recycling where you create a whole new product with it. So that could be done. Maybe nylon from carpet backing, PC from, a manufacturer down the road that was making lenses, they send in and can be used. Kind of unique there too. They have PCs. If you get the good feedstock of it, you can still get clear, which is kind of unique. So a lot of really good options available. And again, this is just a very limited look at that. And so if you need more information, we have one pages that go over a very large breadth of options available. Okay. And then touch briefly on our own product. We call it CB PRYME Eco. So if you're a customer and you've been buying from us for a while, you've maybe noticed if you're buying CB PRYME products, there's a CB PRYME Eco. And so this is our own brand of post-industrial and post-consumer products. In addition to our standard CB PRYME in PRYME or virgin grades, we have these grades that are dedicated to supporting the circular economy. So this is just kind of a little snip of some of the grades. And these are always changing. So as it becomes more important and more people are talking about it, more and more materials are becoming available. So always maybe ask a seller or a tech that you work with what might be available, because it might be totally different 3 weeks from now. So keep that in mind. Okay. All right, so a little chart, our performance versus appearance. So if you're talking property performance compared to our color, we would see or maybe hopefully connect that mechanically recycled grades are going to be kind of the low end of both, because we're just regrinding it. It's got another heat history, and most of the time it's going to be black. So not coloring it too much, and your performance is going to be a little bit hindered. But if it's an application where that's totally okay, maybe that's what you use. Then you have chemically recycled grades, because it's broken all the way back down and then put back into the system, just like it would have been had you done a conventional grade. So better performance and better colorability of it. And then lastly, your bio-based, because all you really did was change out a carbon with a new carbon. So very similar to what you would get out of PRYME performance. So, okay. And then some of these, I'm not gonna obviously go through every section of the table, but some idea of your performance comparing the different types of green to a standard virgin non-green or conventional plastic. So something like a PA6, so your nylon 6s, bio-based versus non-bio-based, you actually see if you look through the whole chart that it is exactly the same, because all we simply did was change out carbons. And so you're comparing it and it's the exact same. So same performance, you're not really giving up much. This would be one of those ones where may or may not be less money, but your performance will not be affected by it. You would just get the green aspect of it, which is nice. Okay, biocomposite performance. So as I mentioned, this would be, we put in a bio-based kind of almost like a reinforcement or a filler. So in this table, I included both copolymer unfilled, so you can kind of see where it's normally performing, and then a glass-filled product, because I do mention it does give you an improvement in stiffness and strength, just not all the way to that of the performance of glass. So you'll see 30% agave, 30% wood maple. You can see specific gravity went up because you're putting stuff in it, but you can see that your tensile strength and your modulus both went up, just not all the way to glass. So your glass being at almost 10,000 PSI strength, you're getting up to about 4.5 with the filled grades. And then your modulus of 681 KSI for glass, and then 300 versus 330. So again, a little bit of improvement, just not all the way to that of glass. So if you need maybe a little improvement over unfilled and still want the green aspect, maybe this could be something that would get you there. Okay, compostable or biodegradable. So again, these are the ones that are being a little more starch-based. So you'll start to see a little bit of some loss in some performance because you're adding starch to a material. So it's not just all plastic anymore. You've got some of the starch in there. So you'll see that there's a little bit of a loss of your compression set performance, specifically at the higher temperatures. So if you're using that and you need that particular property, maybe not a great case there. But if that's not important or that's not necessary for your product, maybe it is a good option as a material to be used. Okay. Post-industrial. So this would be, there's a couple different grades I put on here. So you've got a hybrid, or like partially post-industrial, partially virgin, and then finally full PIR. So you can start to see you lose a little bit of your tensile strength, use a little bit of your modulus, and you lose a little bit of your heat performance because it's going through another heat history. And so you can see you lose a little bit of performance. Still really decent performance overall, but you do lose some of it. So keep that in mind if you're looking to design. Specifically, you've already been making the product in PRYME, and then you look to use a different material. You will see a difference. Okay. And then post-consumer, this one's chemically recycled. So again, it's almost like we made a brand new polymer, which you kind of did. So in this one, you see there's a slight dip, ever so slight, but really very, very similar performance. And so your standard PBT versus a chemically recycled PBT, very, very similar performance because we essentially made a new polymer when we chemically recycled it. So very good performance. Okay. All right, so now we talked about the materials, some of the processes, some of the terms. So now some of the trends that we're kind of seeing a little bit and we get asked about, or we maybe suspect might be coming in the future. So commitments to sustainability. So we're hearing that more and more customers, and more specifically OEMs, are making commitments to their sustainability goals or carbon neutrality timeline, saying, you know, I'm going to be carbon neutral by this date or net zero by this date. So we're seeing more and more of those being made. Some of the difficulties is they kind of make those goals and then maybe struggling the best way to actually accomplish that. And so finding a way to outline exactly how they're going to achieve those goals is a little more showing to be a little more difficult. And so part of that could be using sustainable materials. So if your company has a goal like that or needs something like that, maybe that's something we could help you with. Next would be managing your perception. So that's kind of another big one. So consumers are really pushing a lot of demand here. And so when they're looking for more suitable options, sustainable options, they're also willing to pay a little bit more if it says that it has some form of sustainable option, that it's recycled, that it's, you know, maybe bio-based. They will pay a little bit more for it as well. And so companies are making these, some of these companies are making these goals for brand reputation. You know, everyone's looking for it, so why don't you have a goal for it, right? So they're making those goals. And then some changing regulations. So changing regulations sometimes can hinder your movement there. Sometimes the lack of expertise. So if you don't really have anyone that really understands all this sustainable talk and terms and don't know how to go about it, that can really hinder their goal or their progress to meeting those goals. The other thing that can be a little difficult too is at this point in time, there's a lot of different agencies and regulatory bodies and different kind of regulations or specs, if you will, that these materials could meet or you could try to meet. And so there's no one clear, everyone uses this type or this company to do everything. So that makes it a little more difficult too, because maybe you're looking into something and then the OEM says, oh, just kidding, you know, we need this particular regulation or this particular test. And so that makes it a little more difficult too. And then lastly, some of the market trends we might be seeing. So healthcare is trying to get into it. We've seen some customers ask for some sustainable options for healthcare. The biggest issue here that's going to continue to cause problems is a lot of these grades are not, they do not come with formula lock, which is generally a really large requirement for your healthcare products. And so because they're not holding that, it's difficult to find a material that then will work for those applications. So medical is kind of behind. They're not, they kind of are asking for it. They're maybe trying to get into it, but they're a little behind, as I suspect they might be for a while. And then you have markets like automotive and industrial. So you're seeing a little bit of some push for that. You've got OEMs, automotive OEMs that are making carbon neutral goals. And so we're going to start to see a little bit of push from them in those markets because of that. And then finally, your consumer ones. So because consumers generally are the ones asking for it or wanting to see that goals are there or being met or using particular materials, the consumer market is probably seeing the biggest push and probably the biggest success in using these types of materials. And so we tend to see that most commonly. So those are some of the trends that we are seeing for that and some of the terms. And with that, that's what I had for you guys.
All right. Thank you, Andrea, for your comprehensive presentation, as always. At this time, if you have any questions, please type them into the questions section or raise your hand and I will unmute your microphone. We have Jason Merkel, Technical Manager, who has been with Chase Plastics since 2012, on hand to assist Andrea with questions today. As a reminder, as you type your questions, please complete the survey at the end of this webinar, as your responses will help shape future Chase the Knowledge webinars, and we welcome your feedback. Also, please be sure to check out our blog page at chaseplastics.com/blogs and past webinar recordings that you can watch at any time, and future webinar announcements and registration at chaseplastics.com/webinars. If you'd like to have a custom Chase Knowledge topic presented to your organization, please reach out to Andrea or myself. And Jason, it looks like we have a question on the board for you.
You got it. A few of them coming in now, but Andrea, to start, first question is, what have the PCR and PIR polymers typically been used for in terms of applications?
That's a good question. There's quite a few applications. I would say maybe some type of like storage stuff. Maybe it's a pot holder. Maybe it's anything really that you could get away with using it and lose just a little bit of its performance. And so it would be something that if there's quite a bit of very stringent requirements that are associated with it, we're probably not going to use those. But any type of application where you could get away with it, they might do so. And so more consumer ones, off the top of my head, I'm not thinking of too many, and maybe you know a few, Jason, that you give off the top of the head, but really it comes down to, can you get away with just a slight change in loss of properties, but then still maybe market it as a sustainable product?
Yeah, I can add to that. I mean, frankly speaking, we're seeing, especially PIR and some types also PCR, polymer compounds being used in almost all of the market segments that we serve, with the exceptions of, unsurprisingly, healthcare. Certain aspects of, high-end defense applications maybe doesn't have the tolerances to deal with some of the variability that comes with the recycled product. But everything from automotive, under the hood brackets, engine covers, typically things that are hidden or black because of the colorability limitations of PCR and PIR compounds are being used in automotive, to office furniture. Chair bases and things like that have been made out of PIR and PCR content, not just in the past year, but for quite a few years at this point. Consumer goods, home building and construction, if you're buying a flower pot from a big box store and it's black, there's a pretty good chance that it's plastic, of course. There's a pretty good chance that it's got recycled content. A lot of hidden parts, bracketry, stops, things like that might go into desks or buildings or things like that don't have a high-end mechanical performance threshold that's needed. We certainly see that as well. And historically, we would have said anything that was flame retardant might not have any PIR or PCR content, but as the portfolios of the compounders and the polymer manufacturers themselves, our suppliers, have expanded, we're also seeing them go out and get flame retardant ratings from UL to be able to dabble in different markets as well. So it's currently expanding, but it's certainly not limited in use to one market or one application type. It's pretty broad at this point. Next question, Andrea. Can you comment on mass balance materials, biomass balance, which are typically promoted as sustainable materials in this space? I know we didn't really spend any time on mass balance, but can you give a brief overview?
Yes, correct. And I contemplated putting it in here or not. So mass balance is really an accounting principle. So you'll hear the term a lot. Our manufacturers use it a lot to describe their materials specifically. And so that really comes from an accounting principle. So it essentially says I have a certain amount of green chemicals or products coming in, and I have a certain amount going out. And so it has to do with, we're allowed to blend them. They could come from different sources, but on the way out the door, so supplier selling it to us per lot, it comes with being attached to each individual lot and what percentage it's being attributed in terms of its sustainability attributes. So I have 1,000 pounds of green coming in, 1,000 pounds of conventional, and then maybe I blend it all and I have 5 separate lots going out of 400 pounds each with 50% sustainable, but then it gets attributed to each lot, and they use that as accounting to keep track of, cool, 1,000 pounds green came in, 1,000 pounds technically came out as a portion of it, and that's how they keep track of that. And so it's a really common term that's being used. It's just for accounting, and it's to keep things on the book and keep it accurate for our suppliers, and really for ourselves too, because we'll be looking to utilize that as well.
Yeah, I think to add to that, in most cases, these big polymerization companies, they don't have new infrastructure to be able to have a bio-capable line and a standard, maybe fossil fuel-based line. So they'll take bio-based additives or substitutes and put them right into their traditionally used equipment, as long as it's capable of doing so. So since they're not producing them on independent lines, they end up accounting for a percentage of the whole, and then they're able to sell a percentage of their whole output certified as mass balanced approached. And it's very heavily controlled. It has to be, so that they're not overstating their mass balance capabilities. And we'd like to know up front, when it comes to if a new program is being developed to use mass balance materials, we want to make sure there's going to be enough capacity of the bio-based feedstock to certify that, yes, your annual usage is going to be certifiable and able to be upkept with production in order to certify and have everything really be above board. In terms of polymer types, Andrea, in terms of mass balance, I think we're seeing quite a bit of different options, correct? From, I know, nylons and PBTs and PEI and polycarbonate and polycarbonate copolymers. And anything else come to mind specifically?
Yeah, that would be the general census of what we're seeing most of. Really, mass balance also comes down to certification bodies. Certain certification bodies are certifying that, and they utilize mass balance as their way to certify it. And so any of our suppliers that are going forward with getting certifications like that, so ISCC Plus is the big one. And so any of our suppliers that are going and getting that certification to then use the mass balance as their approach to certify their resins, any of the ones that are doing that are going to be the ones that are going to have your mass balance products. So the big ones, like you mentioned, PEI, different nylons, PBTs, some of the really high-end stuff, maybe some PPAs, HPPAs. So a lot of products are being done that way.
Awesome. Next question, when outlining biodegradable and compostable products, do these correlate to any ASTM or other certifications?
It can, yeah. So the big one would be compostable is per D6400, and that's just the method that states a certain amount of time, a certain amount of it degrading down, so composting down technically in that one, because that's compostable. So there are a few ASTMs associated with it. That one's the biggest one, is the 6400, that states very specific requirements for it to be considered compostable at a certain rate. Biodegradable is just kind of an open-ended, it will biodegrade faster than normal. But generally there's not an ASTM necessarily for it. Whereas with compostable, it's very strict. If you're certifying it compostable, it does have to meet that ASTM.
All right, that looks like all the questions we have on the board today. We would like to thank you all for taking time out of your busy schedules to attend this Chase the Knowledge webinar. We hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Andrea directly. Her information is posted on your screen. Thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar. Happy holidays.